Yes.
All right, so here's the next big thing, and this is torque. So technically, torque, or if you're French, torque, is FR sine theta. So this is how it shows up on your equation sheet, FR sine theta. So the sine theta part is going to be the angle at which the force is going to be applied. So if you look at this setup, all of these, that angle here is going to be at 90 degrees. So what's the sine of 90 degrees? 1, right? So unless you're given a specific angle, you just have to assume that the force is being applied at a 90-degree angle to the surface. So technically, like if I was pulling up like this, like I took a rope and I pulled up like this, then I'd worry about that sine theta part of that angle because I'd only want the vertical component of the force. So, torque. So unless, like most of the time, you don't have to worry about the sine theta part. Is it there? Yes. 99% of the time, you don't have to worry about that part of the story. So, if you look at the units, force is going to be in
Newtons.
radius is going to be in
Meters.
So this is going to be Newton meters. So if you've ever watched like commercials for like trucks, they'll say, oh, it has this, like 500 foot-pounds of torque. So the English system equivalent is force is measured in pounds and the radius is measured in feet. So foot-pounds of torque is the same thing as Newton meters. So this is a situation where you have dealt with torque every day of your life. You just don't know that you have. Literally, even when you were crawling around on the floor, you've dealt with torque. Because every time you have pulled on a handle to open up a door, you have generated torque. So let's look at the variables that play into this. So over here, I've got a 200 gram mass. Over here, I have a 100 gram mass. So if something's going to balance, typically what you talk about is what we call clockwise torque and counterclockwise torque. Okay? So if you're looking at this, remember a clock, like righty-tighty, that's clockwise. Counterclockwise, this will go down back to the left. So if you look at this thing balancing out, the clockwise torque has to equal the counterclockwise torque. That's what allows this 100 gram mass to balance out the 200 gram mass. But what's the equalizing variable? Distance, how far you are from the center. So this is why if this thing is balanced in the middle, which it is, this is why I can have a 0.2 kilogram mass with a small radius balancing out a smaller mass over here that has a bigger radius. Okay? Now, technically, this is going to be force. So how can I calculate the force created by a 0.2 kilogram mass?
Gravity.
Gravity. Oh, that's going to be 1.96 newtons times whatever that radius is. This is going to be 0.98 newtons multiplied by that bigger radius. Okay? So the concept is really simple. So here's where it gets applied. So Colin, turn the camera a little bit over here to the door. Okay. So this is why I said you all have dealt with torque every day that you walk in and out of this room. So there's two ways that I can open up the door. I can push here, okay, out here on the edge, or I could push right here by the hinges. In both situations, is the torque the same? Yep, Sean, you say no. Why? Okay.
But the required force is different to push it.
But is the torque required to open the door the same?
Yes.
Yeah.
So the torque required is the same. If I push out here, Sean, what happened to my radius?
Increase.
It increases. So therefore, with a bigger radius, I can apply a smaller force. True?
Mm-hmm.
Now, I can open it by pushing right here. But what's gonna happen?
Need a greater force.
It's gonna take a lot more force. Why?
Because the radius is small.
I got a much smaller radius. So I can do this, but you gotta push really, really hard to get that door to open. So, this is why, when you look at cabinet, they always put the handles far from the hinges. Why?
So you can open it.
Makes it easier.
You
to
can open it easy. Look at the car door. Look when you go to open up your car door, okay? Where's the handle? It's away from the hinges. So this is why I said you all have dealt with torque even since you were a toddler. Crawling around, you were trying to open up cabinet doors, okay? You all have dealt with torque every day of your life.
I
Now-
got stuck in a cabinet once.
So if you're looking at trying to open up that door, okay? So here's the door. So we said torque equals force times radius. So let's say here's the hinges, right? So if I push right there, I'm gonna have a smaller radius, but that's gonna require a
Greater force.
greater force. If I'm out here, I've got a bigger radius with a smaller force. Now, oddly enough, we could graph this. We could graph force and radius. Okay? So what would the area underneath the force radius graph give you? Torque. So it's just like force times time equals change in momentum. Force times radius equals torque. So if I've got a small radius, guess what I have to have? A big force. If I have a bigger radius, I can have a
Smaller force.
smaller force. But the areas to open up that door would be the same. Okay? Got that. Cool. Okay. Now, with that said, let me hand out the assignment, and we'll talk about that.
So is torque, like when used to refer to like trucks and stuff, is that just like the, on like the drive shaft or?
Yes.
Like
How much torque is available on the end of that drive shaft?
Logo calls they get a truck.
what?
A gift.
They get a truck and you go.
I'm quite excited. Dodge in 2025 is coming out with a plug-in hybrid 3/4 ton truck. I'm very excited about that.
3/4 ton is
Yeah, the
wild.
1500 series. So actually it's a half ton series. But, okay, so let's chit chat about some of these
3/4 ton.
problems.
3/4 ton.
So, if you look on
Doesn't look that.
number one, okay? If you look on number one. So, what's the linear velocity at the tip of the second hand? So if you look on a clock, you've got,
The one clock in a room is gone.
I know, okay, yeah, ironically, the one day I really need the clock, it's not here. So on a clock, you have the hour hand, which right now is a little bit past the 8, and then you've got the minute hand, which is over here by the 4, and then you've got the, we'll even make it ceremonial, the red second hand. Okay, so let's talk bigger idea. How long does it take for the hour hand to make one revolution?
12 hours. 6,
How long?
12.
Everybody cool with 12 hours?
Yeah.
Okay, because yeah, so if you
I
could
was
look at
gonna
a
say
clock,
minutes.
which you can't, so right now it's a little bit past the 8. It's not gonna be back to a little bit past the 8 until 8 o'clock tonight, which is gonna be 12 hours away. So ironically, the hour hand takes 12 hours. Now, how long does it take for the minute hand to go around?
60 minutes.
That takes 60 minutes, and the second hand takes
60 seconds.
60 seconds. Now, in all of them, how many radians is it going to move through?
2 pi.
2 pi. So you know theta over time is going to equal omega. If that's my wall clock, so imagine this is the wall clock. If I model that same thing off of my watch, would any of those numbers change? Why not?
Because they're both going the same amount.
Of
Radians.
radians.
Yeah.
Is radius a factor in this story? No. Okay? Radius is not a factor in this story. So whether it's my watch, the clock that should be up on the wall or not, Big Ben in downtown London doesn't make any difference. They're all going to travel through the same number of radians in a certain amount of time. Cool with that. Now, when you get to question number 1, okay, you got a second hand, 12 millimeters, what's the linear velocity? So when I'm asking, and understand the difference, when I'm asking for linear velocity, that's going to be like in meters per second. Or if I ask for tangential velocity, that's going to be in meters per second. If I just said, hey, what's the angular velocity? Angular velocity is going to be in radians per second. Okay? So, when you get to like question number 4, I said, what is the angular velocity of the Earth as it spins on its axis? Well, how long does it take our rock to spin on its axis?
24
24
hours.
hours.
24 hours. Is that going to be the same for every point on the Earth?
Yes.
Yes. Okay? And how many radians is it going to move through?
2
2
pi.
pi.
2 pi. When you get to number 6 on the front, so let me kind of give you this visual. You got George, mass of 56 kilograms. You got Joe, a mass of 43, wants to balance a 1.75 long meter seesaw. Where should the seesaw balance? Give your answer as a distance from Joe. So, what's different about this problem versus this one? This one, the pivot point's in the middle, okay? This one, you get to pick where you pick or where the pivot point is going to exist. So, let's say here's George, okay? And George has a mass of 56 kilograms. And then you've got Joe over here, okay? Joe has a mass of 43 kilograms. So, imagine this. Here's Joe, and there's George, okay? They're sitting out there on the edges. I get to pick where this seesaw is going to balance. So is the distance, what's going to be the bigger distance? The distance to Joe or the distance to George?
Joe,
Why?
because it has less mass.
It has less mass. So here's going to be the basic idea, is that the torque from George has to equal the torque from Joe. Now this is where it becomes similar to the Lagrange problem. You know the total length of the board is 1.75 meters. So if you let the distance to Joe be x, that's the distance to Joe, x. What's left over for the distance of George?
1.75 minus 6.
1.75 minus x. Then it turns into an algebra problem. Now, just like you can have velocity time graphs, and what does the slope of a velocity time graph give you?
Acceleration.
Acceleration, rate meters per second squared, right? You can have, this sounds funny, you can have a butt time graph, okay? So what would the slope of a butt time graph give you? Angular acceleration, okay? What does the area underneath a velocity time graph give you? Displacement, measured in meters. If you find this area, that's going to be measured in radians. And it's the same idea. If this is an omega time graph and that's 0, is that wheel spinning faster or spinning slower? Over here, on this graph, is the wheel spinning faster or slower as time goes by?
Slower.
Why?
Slow down.
Because you're going to have a negative fish with a positive omega, and you're going to slow down. You're approaching 0. It's just the same idea. So if your velocity and acceleration have the same sign, you speed up. If omega and fish have the same sign, you speed up. Now, just like you can have that equation, v squared equals v naught squared plus 2ax, guess what? This is going to be omega squared plus but naught squared, which is just fun to say, I don't care who you are, but naught. And then you have alpha theta. So basically, anywhere you have v, you can put omega. Anywhere you have a, you can put fish. Anywhere there's x, you can put theta. It's the exact same equations. So when you get to question number 8, okay, spinning 50 radians per second, it's accelerating at 5 radians for 12 seconds. What's the angular velocity? Through how many revolutions will it move? Make a sketch of the angular velocity versus time graph. Okay, this is just a sketch. Boom, make a sketch. Now, when you get to the questions out of the book, okay, on page 218, I'm going to do question number 3. It has to deal with making a wheel spin by applying different torques to it. So in that system, how the book is defining the system, if the wheel is spinning clockwise, that's defined as a negative omega. If it's spinning counterclockwise, that's defined as a positive omega. Okay? So keep that, that's why that statement is there, so that way we're all working off of the same playbook. Okay? And that's true on number 3. There you go. Okay, I'm done. You're on your own, it's Wednesday, and the clock isn't working. So, actually the clock isn't here at all. So
It is 8:27.
all right, so stop yonder camera.